Okay, let's unpack this. Imagine you are trying to build, I don't know, a perfect three-dimensional palace, but you're only allowed to use chemistry. For decades, it was basically the ultimate frustration for material scientists.
Yeah, absolutely.
They were masters of simple, discrete molecules, sure,
Yeah.
and they could build those long, floppy polymer chains.
Right, the 1D stuff.
Exactly.
Right.
But predictable, extended crystalline structures in 3D, forget it.
It really was seen as almost impossible, so much so that, people called it a synthetic wasteland. That term really
A
captures it.
synthetic wasteland. Wow.
And our sources, the scientific background for the 2025 Nobel Prize in Chemistry, they really lay out how difficult this was. John Maddox, back in '88, even called it a continuing scandal that we just couldn't predict how atoms would arrange themselves in crystals.
A scandal.
Yeah.
Because they couldn't design this 3D architecture.
Mm-hmm.
And that failure, well, that's why we're dedicating this deep dive to the material that completely changed the game. Metal organic frameworks, or MOFs.
The breakthrough material.
Our mission today is to really get into the science that earned Susumu Kitagawa, Richard Robson, and Omar Yagi the Nobel Prize. We want to understand how these incredible sort of sponge-like materials are built, and maybe more importantly, what they mean for you, for technology, for the future.
Right. The implications are huge.
So let's start there at the source of the frustration. Breaking that 3D barrier. Chemists really wanted structures with, like, internal cavities.
Yeah, absolutely. Materials that could sort things or store things or just hold onto smaller molecules for a bit. Kind of like natural zeolites do, but, designed.
And historically, there were hints it was possible.
There were glimmers, like Prussian blue, that famous pigment from way back in the 18th century.
Oh, right.
Turns out it's actually an extended 3D framework. It has these voids inside. But nobody designed it that way. It was sort of an accident. We didn't figure out the structure, let alone the rules behind it, until much, much later.
So it showed it could happen, but not how to make it happen on purpose.
Exactly. That leap from accident to design, that really came with Richard Robson in the late 1980s.
Okay, Robson, what was his approach?
He looked at coordination chemistry, the work pioneered by Alfred Werner, and he asked this, well, really revolutionary question. He thought, what if we treat metal ions not just as atoms, but as really precise connectors?
Like joints.
Kind of like the corner pieces in a really high-tech construction set. Could you use them to link organic bits together into a specific planned structure?
Okay, I see. Using the metal's preferred bonding shape.
Precisely. He focused on coordination geometry. He picked the cuprous ion, Cri, because he knew it liked to form 4 bonds in a tetrahedral shape, a really rigid, predictable arrangement.
Like a 4-pointed star.
Exactly. And then he matched that with a rigid organic molecule that also had 4 connection points, a tetranitrile ligand, a sort of 4-armed strut.
So connecting the stars with the struts?
That was the plan.
But wasn't the thinking back then that this would just fail, make a mess?
Oh, yeah. The conventional wisdom, you read it in the sources, was this would probably just make, goo, an amorphous mess. Or maybe a really dense crystal with no space inside at all. Too complex to control, basically.
But that's not what happened.
Not at all. This is where it gets exciting. In 1989, 1990, Robson pulls it off. He creates a crystalline, extended 3D structure.
And it was a structure he predicted.
Exactly. The diamondoid pattern he was aiming for. And crucially, it wasn't dense. It had these large cavities inside filled with the solvent from the reaction.
Wow. So proof that you could actually design and build these things predictably.
Irrefutable proof. It completely changed the game. You can imagine the buzz.
Must have been huge. And Robson saw the potential immediately, right? He didn't just describe the structure.
He absolutely did. He predicted right then that these materials would be stable. Stable enough that you could actually pull the solvent molecules out of those cavities, desolvation they call it.
And the structure wouldn't collapse.
Exactly. It would hold its shape, even under vacuum. He saw it wasn't just a crystal, it was potentially a stable molecular sieve, maybe useful for ion exchange too. That foresight really laid the groundwork for everything that followed.
Okay, so Robson proved it was possible and stable. That really sets the stage for the next phase, the sort of architectural design principles.
Yeah, the conceptual foundation of MOFs themselves.
Let's just quickly define that term MOF clearly for everyone.
Sure. Simply put, a metal organic framework, or MOF, is this infinite repeating network. It's porous, it's built using coordination bonds.
Mhm.
You have two main parts, metal ions or clusters of them, acting like the nodes or joints.
Right.
And then you have organic molecules acting as the linkers or struts connecting those nodes.
Got it. The metal joints, organic struts.
And the whole thing repeats in 3D, creating this highly ordered crystalline material with built-in pores or voids.
And this term, MOF, that became popular thanks to Omar Yagi.
Yeah, Yaki really popularized it in the late 90s, but more importantly, he gave us the design rule book, Reticular Synthesis.
Reticular synthesis. Sounds fancy. What does it mean?
Reticular comes from reticulum, the Latin for net or mesh. So reticular chemistry is basically the science of building these extended net-like structures.
Okay.
It's about using judiciously designed rigid molecular building blocks, as the source puts it, and snapping them together into structures you've planned out beforehand. It's like chemistry meets architectural engineering.
But hang on, if you're trying to build this intricate 3D net, what stops it from just, tangling up or collapsing on itself while it's forming? That seems like the hard part.
That is the hard part, and that's where Yagi's really key insight came in, focusing on secondary building units, or SBUs.
Let's be used, okay?
Instead of just single metal atoms floating around trying to find the right spot, you pre-assemble small, stable clusters of metal ions. These SBUs already have the correct geometry built in.
Ah, so you make the perfect corner joints first.
Exactly. You provide the blueprint and the perfect rigid corner pieces. It forces the structure to assemble correctly, locking the framework into the intended design, preventing that collapse.
That makes so much sense. It shifts the design work before you even start mixing things.
Right. Design comes first. And the result of this control is this powerful idea of isoreticular frameworks.
Isoreticular.
Yeah, iso meaning same, reticular meaning net. So you can keep the fundamental shape, the overall topology of the network exactly the same, but by just swapping out the organic linker molecule for a slightly longer one or a shorter one.
You change the size of the holes.
Precisely. You can tune the size, the volume of those internal cavities with incredible precision. Suddenly, you're not just making a porous material, you're making a family of materials, each designed to grab a molecule of a specific size. Function by design.
Okay, so we have the building blocks from Robson, the design rules from Yagi, predictable static architecture. But there's another piece, right? The dynamic aspect.
Yes, Susumu Kitagawa. He introduced this crucial concept of dynamic behavior. He classified MOFs into generations.
Generations.
And it's the third generation that really blew people's minds. These are the soft, porous crystals.
Soft, porous crystals. That sounds like a contradiction.
It kind of does, but these are dynamic frameworks. They can actually change their shape, their morphology. Their pores can literally expand or contract.
In response to what?
External stimuli, things like heat, pressure, or even just the presence of a specific guest molecule landing inside the pore.
So the material itself can breathe. Flex.
Exactly. A solid material that can open and close its pores on demand. That was a fundamental shift in how we thought about solids. They weren't just static anymore.
Wow. Okay, so building blocks, design rules, and dynamic structures, we can build them, control their pore size, and they can even change shape. Which leads us to the big question. How well do they actually work? How much stuff can these sponges hold? Let's talk performance.
Right. This is where the numbers get really impressive. That huge internal surface area makes MOFs incredible sorbents. They just blow traditional materials like zeolites or activated carbon out of the water for many applications.
And Yagi's MOF5 was the early poster child for this, right?
Yeah.
Back in 1999.
Absolutely iconic. MOF5, built with those zinc-based SBUs, showed a Langmuir surface area of 2,900 square meters per gram.
Okay, put that in perspective for us.
Yeah.
2,900 square meters per gram.
Okay, get this. Take 1 gram of MOF5 powder, like a tiny pinch, maybe the amount you'd put in a small sugar packet.
Uh-huh.
If you could unfold all the internal surfaces within that tiny amount of powder, it would cover nearly half a football field.
That's insane. Half a football field in a pinch of powder.
It's an enormous amount of internal real estate for gas molecules to stick to.
And that was just the beginning, right? They pushed it even further.
Oh, continuously. The drive was always for more porosity. It led to materials like Framework MOF 210.
Right.
That one clocked in with a measured surface area over 10,000 square meters per gram.
10,000. So now we're talking like multiple football fields per gram.
We are. Think about storing gases. If you have that much surface area packed into a small volume, you can potentially store vast amounts of gas at much lower pressures than traditional tanks. Huge implications for safety and efficiency.
And it wasn't just about how much surface area, but also the size of the pores, right? That was a limitation before.
A major limitation. Traditional porous materials like zeolites are typically microporous. Their pores are tiny, less than 2 nanometers wide.
Okay, for small gas molecules, maybe?
Exactly. Good for things like nitrogen, oxygen, CO2, but totally useless if you want to handle bigger molecules. You can't fit a drug molecule, or certainly not a protein, inside a 2 nanometer hole.
Right.
But reticular synthesis gave chemists the control to build mesoporous MOFs, frameworks with larger pores.
How large are we talking?
While structures like IRMOF 74SI were made with pores up to almost 10 nanometers across 9.8 millimeter.
Okay, that's a significant jump.
That's a huge jump. Suddenly you could imagine putting much larger things inside these frameworks. Biological molecules, like proteins, they actually demonstrated trapping things like myoglobin and green fluorescent protein inside these larger pores. That opened up a whole new range of possibilities, especially in biomedicine.
So moving from microsponges to macrosponges, basically. Which brings us squarely to the so what question. What do these record-breaking, tunable, flexible materials actually do for us, for the environment, for the future?
Well, the applications really target some of our biggest global challenges. Take environmental management. Carbon capture is a huge one.
Mm-hmm.
MOFs aren't just sponges, they can be highly selective sponges. There are frameworks like CaLF20, for example, that show an incredibly high capacity for CO2, and crucially, they can grab it even when it's mixed with other industrial gases.
So they can pick the CO2 out of flue gas, for instance.
Precisely. That selectivity is key for making industrial-scale carbon capture feasible.
And what about water? That seems like another critical area.
Absolutely critical. Water remediation is a massive field for MOFs now. We're seeing materials like UIO67 being used to soak up harmful PFAS chemicals, the forever chemicals from water supplies.
That's huge.
And maybe even more remarkably, there's MOF 303. People are using it to harvest clean drinking water directly from the air, even in really dry, low humidity conditions.
Pulling water from desert air, I mean, that could change everything in arid regions.
The potential is staggering. It really is. And the versatility keeps surprising us. There are even MOFs like ZIF-8 being looked at for essentially mining valuable rare earth metals out of industrial wastewater where they're otherwise just lost.
Wow. Okay, so environmental cleanup, water. What about energy?
Big applications there, too. That massive surface area we talked about, perfect for storing fuel gases that are normally tricky to handle.
Like hydrogen or natural gas.
Exactly. High capacity, potentially safer storage of methane and hydrogen. Specific MOFs like NU-1501 and MOF-177 are really promising there. And it's not just storage. They're being used in energy technologies, in batteries, in fuel cells. Plus, they act as super efficient catalysts for making chemicals. Materials like ML-101 are already used commercially in catalysis.
And you mentioned biomedicine earlier with the larger pores, drug delivery.
Yes, that tunability and capacity is perfect for drug delivery. Imagine packing a MOF with a chemotherapy drug
Okay.
and designing it so the MOF only opens up and releases the drug when it encounters the specific chemical environment near a tumor, like a lower pH.
A targeted delivery.
Exactly, minimizing side effects. Plus, they're being developed for diagnostics, for sensing specific biomarkers, and for therapy itself, a whole new class of medical materials.
This all sounds incredibly promising, almost futuristic. But is it practical? Is it scalable? Are these things actually leaving the lab and becoming commercially viable?
Well, that transition is happening right now. The sources are clear that a lot of the early challenges, like stability, especially with moisture, hydrothermal stability, have been significantly improved.
Yeah.
And researchers have made huge strides in making them more cost-effectively and at larger scales. Plus, a big advantage is that many MOFs can be recycled and reused.
Which is important for sustainability.
Absolutely. So the industrial transition is underway. People are now figuring out how to best integrate MOFs into existing materials and technologies, making composite structures. They really are becoming a cornerstone material for advanced technology development.
So just to recap where we've journeyed in this deep dive, chemistry went from this synthetic wasteland where predictable 3D building was basically a dream to a reality where scientists can design, build, and fine-tune materials with these unbelievable internal surface areas bigger than football fields, packed into a gram in pores, tailored for specific jobs. It's a complete transformation of how we think about and make solid materials.
It truly is. And what's really fascinating to think about now is how these concepts, reticular synthesis for precise building and Kitagawa's dynamic frameworks, are starting to merge even more.
Also,
Well, if you have these third-generation MOFs, the ones that can change shape, that can breathe in response to stimuli, imagine materials that don't just passively absorb stuff, but actively respond. They could sense a specific molecule, change shape to trap only that molecule, or filter things in real time based on changing conditions. Intelligent, responsive materials.
wow.
And that raises the big question, right? As the stability keeps improving, as the cost comes down, how quickly will these soft, porous crystals, these dynamic, smart materials, move beyond specialized industrial uses? When do they become fundamental components in, say, our home air conditioning, maybe even embedded in clothing for protection or in wearable medical sensors?
Tiny, invisible, perfectly designed structures working at the molecular level, potentially changing everything from the air we breathe to the medicine we take. That is definitely something worth keeping an eye on.